It may be your car keys, your book, your pen, or your phone, but I'd be willing to bet you search for things almost every day of your life. The same goes with computers. Computers store lots and lots of data, and sometimes the only way to find the data we need is to search for it. Today, we'll look at one of the most basic search algorithms called linear search. Linear search consists of searching for a specific piece of information by walking through an entire data structure one item at a time until we find it. There are no tricks or optimizations here. We just do a straightforward search until we find the information we are looking for. Linear search can be applied in almost any situation, and it doesn't matter whether the data structure is ordered or not. To carry out a search, we generally create a search function. To simplify our discussion, we'll assume that we are going to create a find function that takes as input two parameters, a number to search for and an array of numbers to search. The find function will return the index in the array where we found the number we are searching for. We can return -1 to indicate that we did not find that number, since -1 is not a valid index value. In reality, we can search a one-dimensional array, a two-dimensional array, or some other complex data structures. Now let's walk through the basic process of searching an array. In this example, we assume that we are going to search our array for the number 3. Since we need to walk through the array one piece at a time, we will initialize our index to 0, which is the first element of the array. At this point, we perform our comparison to see if our number, 3, is equal to the item in the array at index 0. In this case, the item in the array at index 0 is 8, so we do not find a match. So, we will increment our index by 1 to look at the next item in the array. We then compare our number 3 against the item in the array at index 1. However, once again, the item at index 1 in our array, the number 4, is not equal to the number 3 that we are searching for. So, we'll increment our index by 1 and perform another comparison operation. This time, the item in the array at index 2 is 3, which does match the number 3 we're searching for. At this point, we found our match, and so we return the value of our index from the function, which is 2. You might be asking, why are we searching for a number in the array if we already know what the number is? That's probably a valid question to ask. Of course, one reason is that we might just need to know if a specific number is contained in our array somewhere. But an even better reason occurs when we are looking for more than just simple numbers. Imagine a case where our array holds complex objects, such as a student or an educational record. In this case, we might search an array of student records based on the name of a student. Then, once we find the student we are searching for, we will also have access to all of the other information about that student, such as their major or current GPA. Encoding this process is relatively straightforward. First, we define the function find with the two input parameters, the number of interest and the array to search. Next, we'll set up the main loop in the algorithm, where we initialize and increment the array index. Notice that our array goes from 0 to the size of the array minus 1. Since arrays are indexed starting from 0, we must make sure we subtract 1 from the size of the array to make sure we don't get an error. Inside the loop is where we perform the comparison between the current item in the array and the number we are searching for. If we have a match, we simply return the index of the array where the match occurred. If we do not find a match, we loop back to the top of the for loop and increment our index to point at the next item in the array. Finally, if we're able to loop through the entire array without finding our number and returning, then we will exit the for loop and return -1, indicating that we did not find our number in the array. You might have noticed that there are actually 2 3s in our example array, and that our search algorithm only found the first 3. But what if we were interested in finding the last 3 instead of the first 3? How would we modify our algorithm? The answer is actually pretty simple. Instead of searching the array from index 0 to index 7, we simply search it in reverse, starting from index 7 to index 0. The way to reverse the loop is actually really easy. We simply initialize our index to the size of the array minus 1, and then use a -1 step to decrement our index down to 0. Otherwise, the rest of the algorithm is exactly the same. So let's see how this works. When the function starts, we enter the for loop and initialize the index to the size of the array minus 1. Since the array has 8 elements in it, the size is 8, and thus we initialize our index to 8 minus 1, or 7. We do our normal comparison, and since the item in the array at index 7 is not equal to our number 3, we simply loop back to the top of the for loop. Then, since the for loop has a -1 step, it decrements the index value to 6. Now we can do our comparison, and since they don't match, loop back to the top of the for loop. Finally, we decrement our index to 5. Now the array value at index 5 is 3, which matches our number 3. The function will then return index 5, completing our function call. So there you have it, a straightforward linear search of an array. Since we basically have to search through each location in the array, it shouldn't be a surprise that linear searches operate in linear or order in time. This should be obvious since the larger the number of items in our array, the more time it will take to find the number we are searching for. Linear searches are really as good as we can do unless we have more information about the way things are stored in our data structure. We can do this by using more complex data structures such as maps, or by ordering our data in the array.